surface integrals of second kind. To consider surface integral of second kind, we have to consider surface orientation first. So let us have some surface. For example, we can take this piece of paper and glue it like this. We will have a two-side surface. We'll have outer side and inner side. But if we take it apart and glue it like this, we'll have what's called a Möbius strip. It is a one-sided surface. So we start here, we go here and here and here, and we get back to the origin without crossing any border. So, how to define it? Let us have some smooth surface omega, and we select point M inside this surface omega, and we move this point, and if there is at least one point that during your way, if you go through here to here, you can find at least one point, so normal vector at the point will point out here and here, so it will point different directions at one point. So this surface is called one-sided. If we cannot do this for any point of omega, this surface is called two-sided. So classical example of one-sided is a Möbius stripe. You can take any other example for two-sided surface. For example, you can have sphere, you have outer side and inner side. And we consider these outer and inner sides only for closed surfaces, so these have to be closed, like here. Now let us have some surface, and it is bounded by some line L. And this is a smooth curve, partially smooth, without any point of self-intersection. So we will choose positive direction of passage if we go counterclockwise. Following this line L, the normal vector will go up here. If we have a surface that has a normal vector specified for each point, then such surface will be called oriented surface. Now let us consider field of speed or vector function p of x, y, z I plus q of x, y, z j plus r, x, y, z, k that flows through some surface. And we have to determine volume of the liquid that flows through part of the surface during some element of time, for per second or per hour. So we can separate this surface omega using piecewise smooth lines into pieces omega I with surface delta sigma I and diameter di. So this will be n parts. Now we select some omega I, and this omega I will have vector ni0, which is normal to mi selected inside omega I. And volume of the liquid that will flow through this omega I part per second will be the volume of curved cylinder. If we will split this omega surface into small enough pieces omega I, then we can approximate volume of liquid that will flow through this surface per second. And if we do this, we can consider this surface planar. Then volume of one cylinder, delta Pi, will be approximately Hi delta sigma I. But Hi, height of the cylinder, is a projection at ni0 of vector A at point mi, which is same as A of mi multiplied scalarly by ni0. In other words, delta Pi is approximately A of mi ni0 scalar multiplication multiplied by delta sigma I. And we can make an integral sum of these parts. This will be A of mi by ni0 delta sigma I. This will be approximation of pi. Now, if we take this sum, I from 1 to n, A of mi by n0 of mi, delta sigma I n0 at mi is normal vector at m0, and we take limit where max di tends to 0 and n tends to infinity. We call this element surface integral of second kind. We can calculate this n0 vector as plus or minus, dependent on the facts if we need inside part of the surface or outside part of the surface, plus or minus gradient f divided by absolute value of gradient f, where f is the equation specifying omega. Taking into account that n0 can be represented as cosinus alpha, cosinus beta, cosinus gamma, or cosinuses of angles that this vector forms with axis of coordinates, then we can transform integral by omega of second kind a n0 d sigma as double integral, a surface integral of second kind, p cosinus alpha plus q cosinus beta plus r cosinus gamma d sigma, or, which will be same, p dy dz plus q dx dz plus r dx dy. Properties of this integral. First one is linearity, that for every alpha beta inside real numbers, integral by surface of second kind alpha a1 plus beta a2 by n0 d sigma will be alpha integral of a1 n0 d sigma plus beta integral by omega of a2 n0 d sigma. Second property, if we have omega consist of omega 1 and omega 2 and these two surfaces does not have any common inside points, then we can calculate integral of second kind by omega as sum of integral of second kind by omega 1 plus integral of second kind by omega 2. And third property is orientation. If we have some double-sided surface, then integral by outer part of this surface will be minus integral by inner part of this surface. There is also one very useful theorem named after Gauss, or you can meet it in different sources as Gauss theorem, surcafe theorem, or divergence theorem, that specified if we have a closed body, closed surface, then we can calculate surface integral of second kind through closed surface p dy dz plus q dx dy plus r dx dy. This can be calculated as triple integral by body g that is bounded by this surface omega, dp by dx plus dq by dy plus dr by dz dx dy dz, and this often comes in handy.